Hello everyone. So today we are going to discuss an important algorithmic concept called backtracking. And backtracking is important because it's mainly used to solve uh, almost 50 to 60% of medium to high level problems out there. So the first step towards backtracking is recursion. So that's why before diving into this topic, you need to review basic data structures and the iterative approaches using for and while loops. So iterative, I can give you like a quick recap of how iterative approaches and recursion works and what's the difference between them. But you need to study them before doing this. Yeah. So when I say iterative approaches, let's say you want to print a string reversed. So when I say reversed, I mean let's say your string is A, B, C, D. Then I want the answer to be D, C, B, A. Similarly, if the string is hi, H, I, then the answer would be I, H. So using a simple iterative approach, you could solve this by using a for loop, which instead of starting at the beginning of the string, would start at the end of the string, and then would iteratively come back one step at a time. So in the case of reversing A B C D, you would start at D and go one step back at a time. So that would be D C B A. But this kind of approach wouldn't work for complicated problems, and that's where a need for recursion arises. So let's see how recursion works and how recursion would solve the string reversal problem quickly. So in recursion, what you try to do is you would try to divide the bigger problem into smaller subproblems until you reach a base case, which you are eminent to reach. And once you reach the base case or the undividable subproblem, you start building up with on the answer from that position towards your top bigger problem. So there are two things you need to know while studying recursion or while trying to solve recursive problems. You need to have a recursive relation. So recursive relation is the one that divides the bigger problem into subproblems. So to reach from this point to this point, you need recursive relation. Again, when you apply a recursive relation on this problem, you would reach this point. So when you go down this road, you ultimately reach a point where your problem cannot be divided further. And this problem is called the base case. And usually we'll know the answer for the base case. And since you know the answer for the base case, you start building up from that position again back towards your bigger problem. So let's see how this works on our problem. So since like I was saying, problem is to reverse a string ABCD to DCBA. And like I mentioned, we need to have two things: a recursive relation, which divides this bigger problem into smaller subproblems, and a base case where you know the answer of the problem. So for me, I've taken the recursive relation as the one where it returns the first letter of a string, no matter what the string is. Even if the string has like 1,000 letters, it still returns the first letter of the whole string. So this is the recursive relation I chose, and we'll see why I've chosen this in some time. And the base case is, so if let's say the string has only a single letter X, so if the letter is X, then the reversal of the letter X would still be X, right? Because it's only one letter. So that is my base case. Now we'll see how we would solve this problem. So initially the string is A, B, C, D. So let's say I applied my recursive relation on this. I would get the first letter of the string, which is A, and the like I showed in the previous diagram, you would apply the recursive relation on the remaining of the problem. And then you go to, so this is the remaining of the problem where I applied the same recursive relation, which is get the first letter. So I applied the relation on this, I got the letter B, and then on the remaining string I applied the recursive relation. And similarly, this is my current string. I applied the recursive relation on this, so I got the letter C, and then this is the remaining letter. And once I reach a single letter, which is our base case, so my base case rule is that I have to return the character itself. So I return the character D. So once I get this, I'll go back again and then join D and C and then join C and B, and which together becomes DCB, and then join A. So this joining operation is the part where I was explaining where you go from base case to the top.
What backtracking is and how it's a better or more efficient way than recursion in solving some kind of problems. So let's consider this example where this is an weighted graph where this value represents the weight between two nodes. And let's say I want the path in the graph where it gives me exactly these weights in strict order. By this I mean that first I need to get the path where the weight between two nodes is 1. So when you consider this parent node, the child nodes, there are 3 weights, 1, 2 and 3. But the first value we need is 1, so I'm choosing this child. And then again, next I'm choosing this child so that I get the next weight to be 2, which is the one we need in our order. And the next one is 3. So I essentially need this path where the weights are in the order of 1, 2, 3. Now, let's try to solve this problem recursively. So in recursion, like I mentioned before, there are two things we need to take care of first, recursive relation and a base case. The base case is simple. The base case can be that if there are no children for any node, then return. That can be the base case. And when it comes to the recursion relation, we can just see like we can like use a simple DFS kind of approach which is depth first search. So where you try to go to the bottom you go to the bottom child and then explore the remaining childs. So for example, the recursion relation could be explore the child of the parent. So when I call that here, I first go to this child, and since I have to explore the child of this parent before going to the next child of the previous parent, I'll go here, and then again I have to explore the child which is this. So in a simple recursion, in the first loop itself, I will get the answer 1, 2, 3. So far it's good. But what if I want the answer 2, 3, 1? This has to be the weight order. In that case, what happens is, still in recursion, I still go for since I have to recurse all the child of the parent, I'll come here. And since I have to recurse on the parent's child first, I'll come here. Since I have to go to the parent's child first, I'll come here. But 1, 2, 3 is not the solution we're looking for. We're looking for 2, 3, 1. So this path is not valuable. Then I'll go back and then I'll go to its second child. And then this value is 3, and then I'll go to its child. This value is 3, 2. So it's 1. Then when I build the answer, it will be 1, 3, 2. And even this is not the answer we're looking for. So this part of the graph is done. And then I'll go to the next child of this big parent, and then the value is 2 here, then it's 1 and 3, which is the one I don't need. So I'll go back to this parent where it has multiple children, and then I'll come back here, and then now it's 2, 3, 1. So this is the answer I need, so I'll return this path. So whatever computations we made in this area of the graph is pretty useless, because we know that the answer we need is 2, 3, 1. Then there is no point in going to the child with the weight 1. So logically, there should be a methodology where as soon as you see 1 over here, you should discard this whole thing, because our required solution is 2, 3, 1, and the first value is not 2, so we need to discard this. Oh, sorry. And then we come to look for the next child, and this which is 2. So as soon as you see 2 which matches with 2, 3, 1, then we start exploring the children of this. And similarly, when you come to this point, it has 2 children, 1 and 3. but the second value should be 3 that we require. So we won't explore this part of the tree, and we'll come here, and there's only one child, so 2 3 1. So you see this, we only choose the ones which are desirable logically. So to implement this, we use an algorithm called backtracking, which essentially keeps track of the output at every position, or at every level of the uh, traversal, and then discards discards the solution as soon as it becomes undesirable. So initially, let's say we choose 1, but what we need is 2 3 1. So 1 and 2 don't match. So we discard this solution and go back to its original state. And then now we have two more options, 2 and 3. And the answer we need is 2 3 1. And 2 matches with the first letter of 2 3 1. So we consider this solution. And then we come here, we have two options of 1 and 3. But the desired solution is 2 3 1, and the second position should be 3. So we discard this value and come here. We discard this value and go to the previous state and look for its children again, and its value is 3. And once we get this, we go down and it's 1. So the simple pseudo algorithm for backtracking is that you start with a solution, you keep traversing or you keep building on the solution, and as soon as it becomes undesirable, you go back to the initial state of the solution. And this is how we usually solve any any algorithm logically, right? Like when we're trying to solve manually by ourselves. So that's why backtracking is so powerful, that it replicates on how we think logically. So this is one of the examples, and obviously when I say we're traversing, that can be done recursively. So that's why recursion is the first step to the backtracking. And what essentially backtracking essentially does is it cuts down the number of recursions or recursion functions we will execute, thereby increasing the time efficiency. Yeah. So let's look at another example where to understand backtracking better. Let's say this is like a 2D matrix, and you want to understand or you want to find the letter SEEC. So let's say the words can be formed. Instead of a crossword, we can use like a simple one where it only the horizontally or vertically. In crossword, you can even use like the diagonal words, right? Let's ignore that for now. Let's say you can only form the words by horizontal or vertical. So in this crossword maze, as soon as you see this would be your output, right? To find this word in the maze or in the crossword. Now, so when you try to solve it recursively, what you try to do is you start from this point, then you'll go to since we can only go horizontally or vertically, then we go to the next possible children, which is B and S. So there can be AB or AS. Okay, and then once you reach this point, you already have AS, and then there can be ASF or ASA. Okay, so since we reach the base case which is we have 3 letters, ASA is not equal to SEE. So we disregard this solution and go back to AB. And then AB has two options, F or C. Then we have ABF and ABC. And ABF or ABC doesn't match with our current thing, so we then go back. Since A is done, then we go back to B. So you see that like this kind of thing is just redundant and useless. But what if we use backtracking? So let's say we start with A again, and then as soon as you find that the first letter S and A don't match, this is not a desirable solution anymore. So we disregard this. And then you go to the next word either vertically or horizontally. That depends on you. So let's say I'm going vertically first and then horizontally. So the next letter is S. So this matches with the backtracking. First letter S. So we don't discard this and then go forward in the traversal. And the next letter is E. So we check that S has no direct contact with E, either horizontally or vertically. So we disregard this key and then we look for this one, and this doesn't work. And then since we are done with this row, we come to this row, and this continues so on. And when you reach the this block of code, or this block of the matrix, you have the letter S which matches with the first letter. So we can go to the next letter in the backtracking stage. And then since the SC is not a desirable solution, but SE is a desirable solution, we match this with the word, and which works. So then we start exploring from this one because the first letter is matched with the output. And then E has two options again, S and E, but S is already used, so we only have one letter E left remaining, which is the desirable solution. So SEE. So yeah, so we find the solution that is required pretty fast. So, but if we were using recursion in this, we would have built the solutions first and then checked if the solution is desirable or not. But in backtracking, what we did is we try to check if the solution is desirable at each traversal stage, and then only if it's desirable we go down that path. If it's not desirable, we'll go back to its original state and try to look for its other solutions. Yeah. So this is how backtracking works vaguely, and like I mentioned, the pseudocode for backtracking is you go down a path. If that path is desirable, you still keep going. If the path is not desirable, go back to its original state or the point where you started. So hope this gives a bit idea about backtracking, and obviously you need to do more practice and like we need to study more. Yeah. So this is the simple algorithm I was trying to explain. So initially you have a starting point, you perform the task, you go down the road, and as soon as it's feasible, you go down recursively and select the next choice, perform the task. If it's still feasible, go back recursively and select the choice and come down. But if it's not feasible, then go back to previous recursive call. By this I mean that go back to the starting position. Yeah. So yeah, this is a bit about backtracking, and for you to clearly understand more about this concept, you need to actually sit down and code one of these standard LeetCode problem, which is finding a word in a 2D matrix. So that's it for today, and thank you.